Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 66. And this problem asks us to draw a stepwise mechanism for these following two reactions and explain why the more stable 2-butene is isomerized to less stable 1-butene, but under similar conditions we get the 2,5-dimethyl-3-hexyne forming a 2,5-dimethyl-2,3-hexadiene. So we don't actually isomerize the alkyne, we actually go down to two different alkene bonds. So let's go over the mechanism for the first one. So from the first problem here, we see that we're reacting with potassium amide. So potassium is just a counter ion, doesn't really do anything, but the real key here is the NH2, which is a strong base, and some sort of equilibrium with ammonia. So we see here that now, what would we have here? Well, we have carbon with 4 bonds, carbon with 4 bonds. This carbon has some protons. So we know that bases can take away protons. So let's do that. Let's use this base to take away one of these protons, making a bond. You make a bond, you break a bond, and those sigma bond electrons will go to form a carb anion. So now we formed a carb anion, negative charge. We have still 2 protons on this carbon, but carbon is not happy to have electrons, not happy to be negatively charged. It likes being neutral. So we will use those 2 electrons to form a new pi bond, making a bond. When you make a bond, you break a bond. So one of these pi bonds of this alkyne will break to form a new carb anion. Now we have another alkene right next to it. And we have those 2 electrons and formal negative charge here. So once again, carbon is not happy to be negatively charged. And if you remember, when we first used our base to pick up a proton, we still have that base with its proton. So we have its conjugate acid. It's actually neutral now. So it's NH2 with H, so it's ammonia. So this carb anion can actually pick up that proton from our conjugate acid to reform our basic catalyst. So remember, you always have to reform your catalyst. So we know that somehow we would have to reform NH2. And now we reform our basic catalyst as well. So we can do this once over again. So this base can pick up this proton, making a new carb anion. So now this carbon has 2 electrons here, but remember, carbon doesn't like to be anionic, so it's going to make a new double bond here with its lone pair electrons. When you make a bond, you break a bond. So now you made a new carb anion. So let me draw that over here. So now you made 3 bonds here, and now you reduce that to an alkane, and then this has formal negative charge. And then you also protonated your base to its conjugate acid. So we know that this anionic carbon can pick up that proton to reform your basic catalyst. So you always have to reform your basic catalyst. And now we form the product in the question stem. But now we see that we have a terminal alkyne. We have a terminal alkyne, and what do we know about this proton? Well, this proton is very acidic. So we know that if we were to use this base again, we can deprotonate this into a carb anion that's very, very reactive nucleophile, but because of the sp orbital of alkynes, this conjugate base is actually highly stabilized and highly favored because of the 50% S characteristic. So this is stabilizing the conjugate base. So it's actually saying that it's okay for this triple bond, this carbon here, to lose this proton. It's okay to exist as this carb anion because it's stabilized by the high percentage of S characteristics. And because it's close to the nucleus, we know that the positive charge of the nucleus, negative charge of the carbanion, they'll be stabilized together. So it's happy to exist there. And not only that, if you were to use this now to do further chemical reactions, we know that doing further chemical reactions, this would drive your equilibrium to your product side. So the formation of this terminal alkyne drives the formation of your nucleophilic stabilized carbanion, which will drive the formation of product. So by Le Chalais' principle, we know that the equilibrium will be pushed to some sort of product side downstream of this reaction scheme. So now let's do the same reaction with the bottom mechanism here, the bottom scheme here. So we'll do that on a new page. So once again, you have proton here, proton here. They're both equivalent. Doesn't really matter which one you deprotonate. But if I use my base again, I can deprotonate one of them to form my carbanion, which will then form your new pi bond here. When you make a pi bond, you break a bond, so then you'll form a new carbanion down there, just like before. And now you have a full negative charge, your conjugate acid, and you remember you need to reform your basic catalyst. So this carbanion will pick up this proton. So what you're left with actually is something that looks like, sorry, let me just redraw this. So something that looks like this. So you're left with this species here. So now you can see that there's no more protons on this side for me to take. So if I were to take the left proton, then I'll just reform my starting material here. So this is essentially the final product as we see in the products here. But why is this isomerized product not as favorable as our terminal alkyne, even though that this forms a more stable product? Well, because there's nothing downfield that can happen with this. This is essentially a dead end. We can't use the base that we reformed to deprotonate anything, because if we were to deprotonate this, we would just form that unstable carbanion. And the conjugate base of this, or the conjugate of this, is not that stable. So we know that this is not an acidic proton, or at least it's not as acidic as this terminal alkyne proton here. So we know that because of the favorable stabilization of this conjugate here, we know, and because of the high S characteristic, we know that this is stabilized, allowing for further products downstream. But here, this is not an acidic proton. The conjugate base of this is not stable. So we know that because it's not acidic, the conjugate is not stabilized. There's actually not going to be any reaction progression downstream here. So by Le Chalais' principle, there's not going to be any driving force to promote this formation of this product. That's why, even though we form an unstable product in this first part, that's why we do form something, because of the driving force to form products downstream.